that go on the limit of knowledge. To moderate, I'll invite Dâmio Hora, please, the manager of compliance of dams in Kinross. Our panelists are Master and Coordinator of Water Resources of Telus, Marcos Felipe Matos Cruz. And Paulo Salah, Consultant and Technical Director of BVP Engenharia Projetos. Dâmio, the floor is with you. Good afternoon, everybody. First, I would like to thank IBRAM for the invitation and congratulate you, Personal Julio and Alina, for the event, the current event. We find we're going to continue the theme of dam break studies, bringing technical side to the discussion, but a theme which is very current. We're going to comment the tailings dams and do an analysis of the dam break strategies in a tailings dam. It's not a new theme. We have been studying this for some time, the questions of dam break studies for dams. As an enthusiast, I have followed for about 15 years, and you see the great progress, evolution in these studies, but there are still challenges. The challenges, many technological modeling, whether in the questions of the characterization of tailings in the rheology, a theme which is very current, and I leave it to Marcos to bring her observations about this, who will talk about dams. Another aspect, tailings dump, which is very current, and they are very current discussions, how to model the dam break studies for tailings dams and waste dumps. That's another question. And let Paula bring her observations, remarks, and invite you to participate. We have a very good discussion, productive discussion. Our theme will be a little different. Our methodology will be a little different. I will bring Paulo Salah presenting with his presentation. Paulo, go ahead. And then next, we'll have Marcos with his presentation about the tailings dams. Thank you, IBRAM. More than that, I congratulate IBRAM because to create these forums where the interest of all, which is the central theme, is mining, it is looked at by different points of view. You have society represented by the regulators, academia, you have the consultants, the mining companies. At these times when you're discussing regulation, especially of dumps, it is really good to hear on the same place the different aspects. Sometimes you go to a conference, it's a purely technical aspect, and you don't see the same gaze that others have. So that is very good for IBRAM to create this forum. Let me talk about dam break studies of waste dumps, as it were. A lot can be applied to tailings, but I'll divide it. I consider, as it were, an estimated frequency, annual frequency of breaches, and we don't have a tailings exposure that you have of waste. Well, the first point that appears here in this is that we have the domain of the generation of geotechnical sections, which are often done at the design phase of design investigations, model is made of a failure and the volume is estimated, and you pass this on to studies dynamics of propagation. So in this first domain of the geotechnical models, you generate a state of limit equilibrium, which is static. And in the case of the dynamic studies, there's a rheology that in a way has a connection, a great connection with the static model, the nature of the materials, the demands they are subjected to, the influence of water. There are two blocks of complexity, and there is specifically in mining, there is even the dynamics of operation of mining. There are the interferences that are done during operation. This often changes the model, the initial model, as was said, the recurrence. By coincidence, here's an example of a recurrence, part of the design, but the operation, the dynamics of the operation can modify this first breach model. The aspects for discussion that I think are most relevant at the moment, we're not to conclude any of them, but the role of the model is to raise questions. We are beginning a discussion that should continue in other forums, and make myself available to continue to debate all these points. The first thing that comes to mind, is there a limit to the height of a dump because of the type of material? I have material A. This material A should have a theoretical limit for its height that I could use or not. That is the first question that comes to mind. The other one is the nature of the material. Is it waste? And the construction method. It is a factor that gets into the design and the studies of consequence of propagation, the reach. The most severe breaches in the world report some dominant causes. We're going to try quickly to mention these causes. As a breakdown of the foundation, how can the foundation affect it? The foundation, we know ahead of time, has had more participation than the material of the dumps. The examples show this not only in Brazil but abroad. But we have to be alert to this. It's a case that I'm going to bring here. Not always the foundation directly. There are, as it were, a material on the slope besides the toe of the dam that might have an effect, a significant effect on propagation and the reach of the broken mass. Just as a matter of curiosity here, I bring an aspect of limit of knowledge. Just curiosity, this interaction of voices and windmills in a turbulent flow, it was solutioned mathematically only 2024. Until 2024, there were several models in different degrees, some more. And this magazine, the Acanta magazine, has a mathematical solution that all scientific community is accepting. We're talking about materials with great fluidity. Basically, they will not benefit in these studies. Before getting into these questions, I think it's worth positioning the facility of dumps with regard to other geotechnical facilities. We have here something which is done frequently in all the books since the 70s. There is a graph similar to this, which the insurance companies like to work on based on frequency by exposure. It's a generic frequency. Each point of this doesn't mean that all the facilities will be within the limits that are here for each facility. There are cases where you are beyond the risk, generic risk, but the generic risk is a starting point. What we see here is that dumps, considering the parameters, I have considered 48% of the waste, iron waste, makes up 48% of the 18.8 billion tons of cubic meters of waste. This is data that began in 2010 and moved forward until 2019 in publications, and I updated them until 2024. We have a 15-year period when iron contributed with 48% of waste, generally with earth. They eliminated rocky waste. Gold is the second greatest, 6.3 of the total, but gold has a lot which is rocky. Sometimes it comes underground, so everything that comes out of the underground mine is rocky. I got an estimated 20-25% of iron waste of the total gold waste that is recorded. Phosphate is the fifth greatest. Why did I put phosphate ahead of copper? Copper in general is rocky waste. Aluminium, which is third place, it's the method of excavating and putting it to the side, and you fill the gaps with stripping, mining, like cut and field, as it were, on the side of a civil engineer. It doesn't create big dumps. The volumes are very big. Discarding phosphate, although I have a total of waste, discarding it, I have not had any news of any breaches of phosphate dump. 50-60 meters of stripping until you get to the ore generates a lot of waste. I get to these numbers. I have the total volume of 1,000 cubic meters for an average of dumps of over 15 years of 232. Number of reported breaches from 2018 till now, 3. I think the first was in Piaba in Maranhão. The second, Cachoeirinha. Everybody remembers that. And the third is Sachinok of Jaguar. Total volume of waste 3.6. Dates, I have 3 orders less than dams, and 4 of dome water, 4 orders of minus than tailings dams. We have a risk almost equivalent to that of aviation, commercial aviation. This is the reality of dumps. 15 years. It influences this because the methods were better over time, both drainage, practice, sending method, and fill. Here I compiled about 100 test tracks or undrained, saturated, and stress strain, and in the end we observe that there are 3 types of behavior, type 1, 2, and 3. Observe the stress strain curves at the bottom. There practically no loss in the strength from the peak to the big deformations. In some cases, the waste type 2, you have a loss and then a gain of strength, which is very typical. And in type 3, you have behaviors which are similar to 1 and 2, with some showing a significant loss of strength to big deformations. Here is a first, as it were, connection, the first rate that we can take from the behavior, generic behavior of several types of waste, almost with 100 tests, a big database. There are more tests than this, but many of these you don't have all the data to set up a database which is acceptable and full. 100 for data and with all the information, also parameters of excess pore pressure. There are, in general, low flow, limited flow, and liquefaction. Liquefaction is a case because only occurs in saturated material, undrained, and shows a lot of loss of strength after peak. We don't see waste with a behavior in this way, except possibly some specific case, where the waste the dump was saturated and the material could have some loss of strength. But in general, we have to be alert with undrained conditions behaving in the foundation. The tests showed the behavior in the flow compacted material. We're comparing materials which are made with thick layers and with vehicles running over them with a practice which is being consolidated, which is the control of the thickness of the layer, moisture, and compaction of this material. So straight off, we expect this has been shown that the behavior of tailings, compacted tailings filtered, is better than waste. What predominates is a low flow. Here is basically the other index, which is physical. It's a relation of desaturation and limit of liquidity. Here's an experiment which is limited with silty, sandy material, 48% of fines within our waste in this plasticity of 5.6 on average. We have 3 zones, one of flow, fluidity, and a zone of no fluidity. If there's no saturation in the material, it all goes into the foundation. The foundation is something we have to be careful with. We always start from the point of view that in the design, the water level in the foundation may rise and affect the bottom drain of the dump. We have to deal with the foundation as if it were saturated. We begin with the principle from design and consider the kind of behavior, contractive or not, in the foundation. The foundation receives the treatment different because we know it will saturate, or you have to consider from the premise that there could be saturation over the years. This is a limit of the height to the question. There is a limit because of the mechanical behavior of the rate of loading. This is an example of the 73 when it was studying all the breaches that occurred, many of them with coal, and one of them was famous in Wales, and there are 144 fatalities. This brought a big impact, and the bishop shows that the material in which he does a loading drained and isotropic is about 0.65. The line on the right reaches a certain level, drained level, then he applies a quick loading, undrained loading. This serves for undrained triggers. What is the sensitivity of to undrained triggers? For example, in the second level of a stress of loading, which corresponds to a height of given height, I have a strength for undrained behavior. Theoretically, because of this experiment, I would have a theoretic limit, and this limit I get to an undrained condition, an isotropic condition. At the beginning of the undrained loading, the material already breaches. I have no reserve to the undrained behavior. Very well. What does practice show us? It has shown there are many other factors which combined which prevailed over the height above the load. All these factors of any number of cases are recorded, are published in the community. They show basically a combination, not of all of them, but some of them. That is the presence of waste that have excess pore pressure because of the grain size, particle size of the original material, the fill and celebration. This is a leader of cases. That's what is most frequent. Blockage of springs and in the foundation and levels of the dump. Many of them don't have a bottom drain. They don't have it. When you talk about it, you see there's something which is very poor, very poorly built. There is a blockage of the material over precious seepage, which will saturate the dump. This is a case that occurs a great deal. You combine the fill with that, they begin to dominate these breaches. Foundation, it has to do with the height. What you expect is that as the height of the design is higher, you remove the soft material each time more rigor compatible with the height there will be.
When you say that the foundation is weak, that means it was allowed to be there in order to reach a height which was not required as the loading capacity, and displacements that degrade the material strength. Here I compare using the same material, coal, so that we don't mix up origins. I have the IBRAM coal mine stack with 66 meters height and 144 fatalities. We have another stack with 400 meters height, also coal, with 800 meters reach and no fatalities. So actually the height is not everything. Here I'm going to quickly present an undrained failure case of the natural slope in front of the pile-toe. On that image you can see the scar of the failure. On the blue line you have material that comes from the stack, and the red line has no stack material. It was a failure that was induced by rapid loading that the stack caused beyond the stack toe. Here on this side you have the displaced material on the stack failure. It advanced 120 meters beyond the toe. If we were to analyze comparing effective parameters, the dark brown material acting on that material on the bottom, I have effective parameters with a much smaller surface. There could be a failure that would advance a little bit beyond the 120 meters failure generated by the stack, but respecting the volume that's in that circle with 1.06. Here, based on images, we start seeing that things are a little bit different. We have the cyan part, which is stack material. In red, it's induced by the rapid overload of the stack with undrained contractile material. And you also have a progression that advances beyond the blue area, that blue boundary. And reaching a conclusion that a slope with 20 degrees declivity, a smooth slope, and a failure with such a load, I can only explain that it's an undrained failure. We performed an analysis of the undrained failure, respecting those limits. See, I have the limit of the reach of 120 meters of the stack material, and then later I see a progression of another 500 meters due to the failure. That's the position that we call complexity. We would hardly expect such behavior. The first failure would be completely within the operational area. The second failure advanced another 500 meters ahead. The first failure is explained due to effective parameters, and the second one is only possible to simulate it for a natural slope of 20 something degrees of a slope of 20 degrees. The highlights here, if there are height limit for stack, the notable failures were due to a fill crest and absence of underdrain, and then a weak foundation. This goes to show how we should imagine a failure of disposal of fill crests. From a slopes crest, you can dispose of complete segregation of the material, as you see there, coarser on the bottom, and it conditions all of the water flow. It is extremely unfavorable. And just for comparison purposes, we have different cases from the world. I base myself on to obtain those causes. Usually, these are the curves. I have sandy materials with up to 3-inch chips, and in most cases around the world, especially when it generates fill crest. And how the composition and behavior of the foundation can affect. They can be more influential than the slope. We know that the classification systems set the slope angle as a negative parameter, but we see a failure in a 20-degree natural slope due to the undrained behavior. Slope is not everything. Composition and behavior of the material is important. It's very hard to obtain predictability. And the probability is generic as well. And the first probability and frequency graph is basically a generic frequency. There could be cases where those dots migrate to other areas. I'm undertaking more risk, and that point displaces to the project. Generic statistical probability not taking into account individual characteristics. Thank you. Congratulations, Paulo. I'd like to invite Marcos for his presentation. And now we're going to talk dams, so please feel free. And I encourage everybody to ask your questions. A lot of technical stuff to talk about. Good afternoon, folks. Let me say thank you for your attendance and for the opportunity of being a part of the event. I see a lot of friendly faces here. And to be a part of this event with such amazing people and so many, important faces here as well. As Daniel had said, the idea was to talk about dams and stacks. I'm going to talk about dams when I had access to the content or the title, situations that navigate in the boundaries of knowledge focusing on dams. I thought, how am I going to convey this information to you in a way that it doesn't stop here, it goes beyond this topic, remains being reflected upon. I chose not to focus on one single technical topic, but in a much more general and encompassing way so that we can permeate these situations that navigate in the boundaries of knowledge. To begin, I'd like to begin with a definition of a dam break study. Everybody here knows how a dam break study works, but a dam break study seeks to subsidize the understanding of the phenomena and the extension of damage in case of a dam break. The use of the dam break study aims to mitigate the effects of the dam break. In order for us to connect this definition and the title of the panel, there are three questions that are going to help us to brush on this topic. Where are we in terms of understanding the study? Up to what point the studies are accurate, and what are the analysis points, and how to deal with the results obtained beyond the obvious? These are the three questions that are going to help us correlate the definition here and the title of our presentation. The fact is, we know how to develop a dam break study. We know the procedures, we know the techniques. Everything is under our domain. There's nothing new about how to do it. But based on the guidelines, legislation, and acquired knowledge, this point is something that's agreed upon. It's also a fact that we had notable progress in the last 15 years. My friend Leonardo Mello, he's here, was the first person I saw back in 2009, maybe, developing a dam break study. And how did we do that, or how was it done? We left a one-dimension study with Newtonian fluid, and today we are doing 2D, 3D studies, taking into account the tailings and rheological characteristics. There was a notable evolution on how to develop a study. So where are we now? We are here. We can generate a flood map, and the study includes the hydrological, local and regional characteristics. It also includes geotechnical and rheological characteristics and all the available technical support. We added there in order to have the best possible study. That's where we stand today. The first question, where are we today? There has been context made, everybody now is on the same page, so now we can go on. Up to what point is the study accurate, and what are the analysis points? Just as I said that we know how to do a study, we also know that there are many different attention points when it comes to the parameters and entry data considered. And this is a very important situation because you will see in the next slide the parameters considered in all the entry data, they interfere profoundly in the study results. So we need to understand that the study, even though we know how to do it, the entry data and the parameters used are going to change, and we need to understand what's the repercussion so that we can answer the third question. For example, the natural flow rates consider the return times, especially the return times for natural floods that come from a rainy day. Are they adequate? Is 100 years an ideal return period for some basins? The regionalization that's used for us to manage to use the entry points for flow rates and points of interest, are they being set with stations that can give us a good support for regionalization? Another situation, the Brescia characteristics. Even though we have technical support that allow us to calculate and understand the hydrograph, are we understanding if the breccia is going to happen exactly where we established at the time that we established. It's the generation of the hydrograph according to legislation. That's another analysis point that we need to take into account. The rheological features the behavior of the tailing in different depths of the reservoir. Our analyses are made in surface or subsurface situations. And what's the behavior of the tailings in the reservoir at deeper depths? Are they going to behave the same as the tests showed us in more superficial situations? That's another situation. You're navigating at the limits of the knowledge, at the very boundary, and we need to take that into account. Another situation here, the topographical base of the downstream valley, as well as the digital model for the terrain. We know that the situation also interferes. This is under our domain of obtaining information that's more accurate when it comes to the topographical survey, as well as the digital model generated. And also, we are also talking about roughness here, another parameter that interferes in the parameters used in the modeling. Up to what point is the study accurate and what are the analysis points? To answer the second question, we have a few pieces of information. All the points mentioned previously interfere in the result. We are on the same page about that. What's the state of the art here? Application of all of the available technical knowledge and the performance of the sensitivity analysis. We should do the sensitivity analysis on the parameters to understand how they reflect on the result. And this takes us to the third question. The assessment from engineering is fundamental for us to be able to deal with the data we have. They can undergo this variation, as well as allowing us the limits and the understanding of the phenomena be conducted. Engineering is fundamental when it comes to using information properly. Remember from the beginning the definition of a dam break study? A dam break study aims to provide support to understanding of the phenomena and the extension of the damage a dam break would cause. Summing up what we discussed so far, contextualization of where we are and up to what point the study was accurate, we can actually be compliant to what's being put up as the objective of the dam break study. The study, is it well done? Can we carry it out? We also know what goes on if we don't use the information properly, the information from the study. Now the third point, how to deal with the results obtained in the study. Besides the obvious, do we know how to do it? Do we know the procedure and techniques? Do we also know about the uncertainties? And we use the engineering judgment to make the study proposal feasible and make the results safe. We also should analyze the result taking into account the existence of these factors and not as a result of a centimeters accurate precision. How to deal with the results beyond the obvious. So, how does this dam break study can be used? We develop a study, we have a flood map, and the flood map, according to the results, can be addressed as accurate or not. So if the flood map is crossing this area. If I'm here, I'm good because the flood map is not reaching where I am. But we know that there are many parameters that interfere the result profoundly. In this case here, we can see people here right on the border of the slime. And we also see some people here next to some buildings. What I mean by that, you know, is the following. When we develop a study, we're going to define a flood map, but those people here, were they trained in an emergency response plan? Have they taken into account, for example, that the flood map would take 10 minutes to arrive there? Were they trained? Did they know that in 10 minutes the slime would be there? What if it's not 10 minutes? What if it's 8? What if that guy that was a part of the training is trained? He had a fishing rod and he heard the siren and he thinks, well, I was trained, I know I need to go to a meeting point, but I'm gonna get my fishing rod because there's time, because it's only in 10 minutes. The limits of the safety zones definition are we need to have a safety margin. Safety margin. Precisely because if we're going to take this to the letter, the definition of a flood map, we could see situations such as this hypothetical one that I mentioned, simply because once the flood map is here, I think I'm okay, I'm not going to be penalized. And here, another situation for us to assess the result of the dam break, how to go beyond the obvious. If we develop with dam break, we're going to get very close to this. Not going to be much different from this. What we effectively had as a result of the flume, but this precision regarding these details, we need to think about it a little bit because most likely these points are not going to be very accurate. The accuracy will not be as high. And to wrap it up, the limit about the knowledge on this topic brings us a few topics, few questions. Where are we in terms of understanding of the study? We know that we know how to do it, we know the procedure, we have the technique to do it. Up to what point is the study accurate? What are the analysis points? With the engineering knowledge added to the technical knowledge, we have consistent points and we can reduce uncertainties. We know that this could change the result. We need to take this into account. And the third question is how to deal with the result obtained beyond the obvious. We need to take into account that the result of the study should be addressed, parsimoniously, putting into evidence the limits and information pertinent that have been presented. The three questions posed for us to conduct the presentation have been brought up so that we can reflect upon that together. What are the possibilities here? There are a lot of opportunities for us to navigate in the limits of knowledge, for example, deepening rheological knowledge and the propagation of the mobilized volume. Especially the rheological knowledge in the reservoir at different depths. This is very important because how are we going to be certain, or today, how are we going to deal with the situation? The engineering knowledge based on the information that we have leads us to a conservative scenario, but that allow us to be safe enough in using that parameter. We need to keep on progressing, insisting on technical improvement, because we're always going to be at the boundary of knowledge every time we advance. We need to keep on making progress and delivering more accurate and assertive studies. That's all. Thank you. Congratulations, Marcos and Paulo, for your presentations. Thank you for the questions. I'm going to ask a few questions now. We have a question from Zeneto within that aspect that we mentioned. We've got dams, we've got stacks, and Zeneto gave us a different approach within the dams. We have a different situation in terms of operational aspects. We have a question for Paulo as well. What are the methods that are appropriate and supported for a dam break study for decharacterized dams? What are the challenges and opportunities? In a question that the dam break study is always being, we always discuss it with the geotechnical team. They gave us all of their support, but we're moving on to stacks now. And decharacterized dams, an opportunity to engage further geotech in the characterization of the failure mode and all of the dam break studies of those two things, decharacterized dams and stacks. Let's talk about the methodology of the dam break study. The decharacterized dam, they're going to use the same same knowledge base as operational dams, in the sense that we're going to have to define the characteristics of the material, the volume, rheological occupation that will support the study. There is no difference in the way that we study a decharacterized dam. We're going to do it the same way with the same principles and methods, but we're going to take into account the current state of the dam. Now I'd like to ask Paulo, do you identify in those two scenarios an evolution, a better use of geotech in those two scenarios? Do you mean the scenarios of a dam break and the characterization of the dams? Well, for stacks, yeah, I believe so. In fact, sometimes by intuition you think the height is the worst element. The highest the stack, the worse it is, but we just saw that it's not true. Some other elements have an influence there as well. And then we start seeing that height is not everything. And a lot of what we've seen, there isn't a lot of records of waste dumps, but most of them show clearly that operational factor has an important factor, an important influence. What will you project and what you're going to get in terms of operation or performance of the works or the characterization, that's a big gap that you need to use recurrence. Those two things, they are bound to each other. The operational mode has a lot more of influence. I wanted to compare it to height. And other thing is the complexity. They are not being leveled during the project design. How is the material beyond the dam toe behaving? Sometimes we're concerned with the foundation, but then you find out there's another element that amplifies the progression of the broke material. That they're known, but they're not as evident. Okay, very good, thank you. Now a question from Eduardo. When it comes to the stack failure, can a dam break study or stack break study give you a mass displacement figure? How critical is this scenario? These are very sensitive parameters, both when it comes to the stacks, and we are making good progress on the stack break study, but also the rheology. It's well in line. How do you see the sensitivity analysis to address those topics, those uncertainties, Marcos? I think it's fundamental to perform a sensitivity analysis. It gives us great potential of understanding of where we have a gap, what could happen, and whether that parameter I'm using is a little bit different, what happens. What if it's very different? Does it give you a result that's going to impact that first result? The sensitivity, when we are not very certain, or when we have such a huge universe of information, such a vast one, that will allow us to be safe when using that parameter. It's fundamental when it comes to understanding a much deeper way how that structure is going to work.
With regard to time of propagation, the reach, yes. Very briefly, well, I think time will depend on the rheology, fluidity, but the capacity of reach. What we try to show as an example, and here I'd like to thank Jaguar allowing us to bring this data that brings for us an illustration, very interesting illustration, which coincides with our theme, which are complexities. I believe that very often when there's a sump and the more granular material of the dam, but the rheology, more granular, less water, less, it will have a breach much closer. And this proximity time, if we're talking about 500 meters, time has a lot to contribute in this. But when you bring about 700 meters, especially if in the 700 meters you're beyond the limits of the operational area, time begins to weigh. I think it's very much linked to two things. The phenomenon, mechanism, the more participation there is of water reduces time, and the rheology you apply for this. Rheology that you attribute in your model and which allows in the programs, computational commercial programs, make an association with time. Obviously, kinetic energy has a participation, but the rheology and the mechanism which command this. Otavio asked a question. I don't know if I'll say it correctly, Otavio, the name of the mine. The leach dumps as like the bridge of Coppola in 2024. Could there be an example that show the importance of undrained tests? Did I say the name of the mine correctly? I think you're referring to Turmalina of Jaguar, is that right? Well, that wasn't a leaching pile. It was filtered tailings. With filtered tailings, But I think what he is referring to maybe is some desegregation chemistry that the material might undergo. For example, there are cases where the material is more fragmented, more granular, but it undergoes desegregation where the mechanical, but very often because of oxidation or sulfates, this kind of thing. This in fact affects it because it affects the nature of the material. Now, the undrained, drained will depend on the water. The case which we know, the water level wasn't high. The water was more important in the foundation, the behavior of the foundation. Marcos, you commented in your presentation about the judgment of engineering. How do, with the technical objectivity demanded by the and the public affected by legislation or by the, we're working with very sensitive data, as we said. We have limitations, even technical limitations, for characterization of the material. And what generate these uncertainties? How can we work and weigh these questions about engineering judgment? Well, engineering judgment, it helps us to have a guide to legal compliance. Why? First we have guidelines which have already brought, but if we have data, but not data so vast as I said previously, we're going to need, within the universe of information that we have, in the best way possible, understand that and direct how the study will follow so that it complies technically, gives us the support, technical support, which is required, and it agrees with the dam that we're looking at. There isn't a formula, but we need to put on the table and identify, make these factors, the points that I raised here, the best way possible. How we're going to comply. There's no formula, but we need to try within the 3 points, put each one in their correct measure. Leonardo raised a question here. The mobilized volume of this instability with the lowest factor of safety. How do we consider false scenarios of greatest credible and improbable factors? This is one of the secrets, yes. That's the million-dollar question, yes. Very often, the project moves forward to such a point and works very often with, even with hypotheses which are more conservative, and they ends when it shows the factor of safety that was reached in the hypothesis and that it's okay. If we were to think only for the design, you wouldn't have these breaches. That is, once you begin to be credible or not, obviously it will depend on the extra phenomena that you're considering. Think that we hadn't considered any undrained breach. We would have to put quakes or increase the water level, the hydrostatic component, the vibration of quakes. That is very common. That you will worsen everything until you get to the mass with a low factor of safety, indicating that it propagates. I believe the credible, it is applied for this. When you have to worsen, deteriorate the situation a lot beyond what the design sees as conservative. But we see sometimes the phenomena that were not thought up, they could because they're cases that appear, and we have to learn with these cases. But there is, in fact, it's always something that we find. What is credible and what is credible. Sometimes you go to something that is beyond what is normal down one path. The other path takes you to something which is credible however, with the lowest type conservative hypothesis. We have to understand the the participation of water. If you make a mistake when the material doesn't have participation of the water, the reach is lower, less. The error may be punished less. As you have more participation of water in the phenomenon, in undrained behavior, greater fluidity, the mistake punishes a great deal more. It's not a simple thing at all. Credible is something which covers a lot. It's a word that covers a lot. It depends how we're applying it. Very well. I think finalizing the contribution of both a question considering the legal A&M decision, the objective of these PABM studies, what's the sense of discussing a failure mode? Are we going beyond a limit? That is a question which is the failure mode. It is part of the whole process. It can define precisely, or it will define precisely, what volume will be mobilized because of this mode that is being considered. I see it as important for us to discuss it. It is part of the process. For me, the question isn't very clear. The failure mode is part of the process. It's within the process. You study the impact from some hypothesis, and we said the hypothesis that exceeds what the design, because the design has to say my worst factor of safety is 1.3, case A, B, C, adding all the factors that may be at play, but you can't eliminate the failure mode. It's not clear to me what will be the focus of the question. Go, folks. Because of the time, we could have a lot of discussion around this aspect, especially with the stack break, with the being very widely discussed. Also, move forward on the dam break studies. We have to move a long way forward in characterizing tailings numerical models for this kind of material. The theme, I think, is long. It provides many hours of discussion. But let's close now. And thank you, Felipe. Thank you for the question, for your participation. Thank you, Paulo. Thank you, Marcos, for your partnership and for the discussion. Thank you. I place you stand for the official picture. While we do the picture,